So, good morning, everybody. Shall we start? I'm not sure the microphone is adequately adjusted, but let's see. All right. So let's see. What did we do? What did we do last time? We finished our discussion on Bernoulli's equation, and in one variant this will go on today. And then introducing the discussion of shocks. I first talked about the method of characteristics, and then we used the method of characteristics to see the one crucial statement that we are going to need, namely that perturbations, density perturbations, pressure perturbations in a fluid will travel faster in denser media. Travel faster where the fluid density is higher. And this leads to the steepening of sound waves and ultimately leads to the formation of discontinuities. This was the main statement. By the way, I hope that the stream and the recording are going to work. I have no idea, but I did the same things as I do in the other lecture hall, so hopefully it's going to work. All right, that's where we were. And discussing the method of characteristics, we found that the characteristics in a fluid are the Mach cones, the lines that show how sound waves propagate. And that along characteristics, we have conserved quantities, namely the so-called Riemann invariants. And we use those to arrive at our crucial statement. All right, so far so good. Do you have questions up to that point? If that is not the case, then let me continue with the discussion of shocks. Stoßwellen in German. So something must happen, right? We start with a perturbation like that. And then as time proceeds, this will turn into perturbation like that. And then we will have discontinuities in the density, in the pressure, in the temperature, and so on. And we need to find out what the amplitude of these discontinuities is going to be. So I'm imagining that if this is the density, for example, upstream of the shock, and there's the shock, the density downstream of the shock. And I want to know, this is rho 1 here and this is rho 2 here. I want to know what is the ratio between rho 2 and rho 1. That's legitimate, right? Do you remember this picture of the galaxy cluster that I showed you in the beginning? There was a feature in this galaxy cluster in the X-ray emission that looked like that. And there was high intensity here in the X-ray image and lower intensity somewhere else. So there was a jump in the intensity, and we want to interpret sudden changes in images like that. Okay, so let's see what we can find out. We will use exclusively conservation laws. And we have 3 of them available. That's the conservation law of mass, of energy, and of momentum. And we will see that using these 3, we can derive essentially everything we want to know about the shock. All right, now how do we formulate that? We will assume that we have a so-called orthogonal shock, right? A plane orthogonal shock. So what I'm assuming is that a plane discontinuity is traveling through the medium along the x-axis, and that we have no gradients in the y and z direction. Right? So we have a plane shock wave that travels along the x-axis, a plane orthogonal shock. In that case, I can write the matter current just as rho 1 v1, And mass conservation tells me that on both sides of the shock, the matter current must be the same. Rho1 V1 is Rho2 V2. Okay, that's mass conservation. Then we need to have energy conservation, and therefore I'm going to equate now the current densities of the energy on both sides. And remember, the current density contained a lot of things. It contained the kinetic energy. There's going to be a factor of rho, but the kinetic energy density. We had the specific enthalpy. I think last time I wrote this down, it was epsilon plus p. That's the enthalpy, the specific enthalpy, enthalpy per unit volume. And then we need to multiply this with Rho1 V1, because this is the transport of the two types of energy, the enthalpy and the kinetic energy. And this must be the same on the other side of the shock, so this is V2 square plus H2 twiddle times Rho2 V2. And you see, since mass conservation requires us to equate Rho1 V1 with Rho2 V2, we could just as well equate the parentheses. All right, and then we have momentum conservation. And for that, I'm going to equate components of the stress energy tensor. Now, I do not need to equate all the components of the stress energy tensor, because in the situation that I am considering, right, where we have a matter flow along the x-axis only, the one component of the stress energy tensor is the only component that matters. So I'm going to write this down. This will be Rho1 V1 square. That's the ordered contribution to the stress energy tensor, plus P1 equals Rho2 V2 square plus P2. Okay, so these are the three conditions that we need to satisfy. But remember, we made the crucial assumption that we have a matter flow along the x-axis only, and that we have a plane perpendicular or plane orthogonal shock. Right? If you have a curved shock, such as this, or you have a matter flow that is not perpendicular to the shock, you will have to take into account that you have a tensor equation here, you have a vector equation here, you have a vector equation here, and then you need to take into account that there can be misalignments between the matter flow and the normal direction of the shock. All right, but let's make it simple. Let's do it like that. And then we have these conditions here. All right. In addition, I'm going to introduce certain approximations, or no, that's not true, certain abbreviations. I'm calling Rho2 over Rho1 equals R. R is the quantity that I want to find out. R is what we want to solve for. And if we define this ratio R like that, we immediately conclude from continuity that this is also V1 over V2. Right? Okay. Then I'm introducing another quantity for the pressure. P2 over P1 equals Q. Sometimes you may want to know Q. Okay, good. We are going to eliminate Q on the way towards R, but nonetheless. All right. In addition, I'm going to use the following relations. The Mach number is V1 over CS1. Okay, that's just a definition. The specific enthalpy is CS1 squared divided by gamma minus 1. Now, how do the sound speeds relate on both sides? what if I now want to know CS2 squared? Well, you know that this is gamma P2 over rho 2 under adiabatic conditions, right? That the adiabatic sound speed squared. And now we can write this as gamma P1 over rho 1 times P2 over P1 times rho 1 over rho 2. The first two factors are the sound speed CS1 squared. Here we have Q, here we have 1 over R. So in this way I can relate the sound speed on the other side to the sound speed on our side. And this also means that H2 tilde is going to be H1 tilde times Q over R. Assuming that we have the same adiabatic index on both sides of the shock, which does not need to be the case. Right? The shock can lead, for example, to dissociation of molecules. Then we are going to have different matter, different types of matter on one side than on the other. Then the adiabatic index may also change. We ignore that for now. Okay, but I'm going to use that H2 tilde is going to be H1 tilde times Q over R because of that relation here for the sound speed squared. What else do we need? In addition, since I'm going to divide equations 2 and 3 by the sound speed square as we go along, I need to, and also by rho 1, I need to know how the ratio P1 of P2 over rho 2 is going to relate to P1 over rho 1. So first of all, this is P1 over rho 1 times Q divided by R. That's the same logic as we just applied. And you see P1 over rho 1 is CS1 squared divided by gamma. I'm going very hard to try to distinguish gamma and R. Maybe I should use different colors for them. Okay, these are relations that just follow from what we already did the last few times, which I'm now going to use as I'm going to apply, I'm going to draw further conclusions from these equations. Now, equation 1 we have already used. Right? The only statement that equation 1 allows us to make is that the ratio of V is the inverse of the ratio of rho. Okay, fine, we know that. Now, I can cancel these terms here because of continuity. And now we have used continuity and don't need it anymore and can throw it away. Okay, now I'm going to divide the first equation by CS1 squared. So then I'm getting the Mach number squared divided Mach number M1 squared divided by 2. I divide this by H1 tilde by CS1 squared. This gives me 1 over gamma minus 1. On the right hand side I now have V2 squared divided by CS1 squared. But V2 squared is V1 squared over R squared. So this is just M1 squared over 2R squared. Then we have H2 tilde divided by CS1 squared. So this is H1 tilde divided by CS1 squared. So 1 over gamma minus 1 times Q over R. Okay, that's all that energy conservation tells us. Now let us see what momentum conservation tells us. And in order to do that, I'm going to take the energy conservation equation, number 3 here, and I'm going to divide it by rho 1 times CS1 squared. So then, I start with m1 square here. Then I have P1 over rho, no, sorry, P1 divided by rho, yes, over rho 1 divided by CS1 squared. That's just 1 over gamma. Right, because of that. And on the right-hand side, we have rho 2 V2 squared divided by CS1 squared. This is R times rho 1. This is V1 squared divided by R squared. So this is rho 1 V1 squared divided by R. Okay? So if I divide by rho 1 CS1 square, I'm getting M1 squared divided by R. Finally, I have P2 divided by rho 1 CS1 squared. Let me do this over here. P2 divided by rho 1 CS1 square. That's what I want to know. So this is Q times P1 for P2 divided by rho 1 CS1 squared. But P1 over rho 1 is CS1 squared over gamma. So that's just Q over gamma here. And that I need in addition to that. And then I'm done with the next step. Now, I'm doing the obvious thing, right? I'm multiplying this by R times gamma minus 1, and I'm multiplying this by gamma. Because remember, our goal is to find out what R is. And so we are going to eliminate Q. So I'm going to isolate Q in both equations and move on. All right, so what follows is M1 squared divided by 2 R times gamma minus 1 plus R equals M1 squared divided by 2R gamma minus 1 plus Q. That's what follows from the first equation. And from the second, if I multiply this with gamma, I get M1 square gamma plus 1 equals M1 square divided by R times gamma plus Q. And now, of course, I'm going to subtract one from the other. Let's subtract the first from the second. And we will arrive at an equation exclusively for R. So M1 square gamma minus, let me just write the terms as they come, M1 square gamma minus M1 square divided by 2 R times gamma minus 1. Now, plus 1 minus R, that was the left-hand side. And I'm intentionally not combining the M1 square terms. I have something different in mind. Now, M1 square R gamma divided by R times gamma minus M1 square divided by 2R gamma minus 1 and nothing, right? Because the Q's cancel. Okay, so this is now our combined equation, which contains mass conservation, energy conservation, and momentum conservation, and is one remaining equation for R, given M1 and the adiabatic index. Okay, now let me multiply this equation by R, then I'm getting a quadratic equation for R. So I first collect all terms that will turn into R squared. I'm going to have minus r squared m1 squared over 2 gamma minus 1. That's this one. And I need that one. That's going to give me a plus 1 because I have pulled the minus r squared out. Okay, now we have the quadratic term. Then we get a linear term from all the terms that are now constant here. So this gives me plus r m1 square gamma. That's this one. Then I'm getting that one. So plus 1. And then all that is left are the terms that are constant in r. And I'm going to bring them on the other side. So this will be plus m1 squared divided by 2 gamma minus 1 minus m1 squared times gamma equals 0. Okay. Now we just need to solve that for r, and we are going to be done. However, before we do that, let's simplify this a bit. You see here I have m1 squared times gamma divided by 2. I'm subtracting m1 squared gamma. So this is going to be minus m1 squared divided by 2 gamma plus 1. Okay? Now, let's multiply the equation with minus 2 to make it even nicer. Then we have that, that, and that. And that. Or that. Okay? So, we get two solutions. They are 1 over 2 times m1 squared gamma minus 1 plus 2 2 times m1 squared gamma plus 1 plus or minus. Sorry, I need to go to the next line now. Square root. This thing squared. And now minus 4 times this thing. Okay. Now we just need to beautify this a little bit. If I take m1 squared gamma plus 1 and I square that, and I subtract m1 squared gamma plus 1, a little miracle appears. Oh, sorry. It's not complete yet. 4 times this times that, right? Now it's complete. So, now I need to see what that is, right? Just the expression under the square root. Okay. You see that here I'm getting m1 to the 4th power times gamma squared plus 2 times gamma m1 squared plus 1. But now I'm going to subtract the product of these two, and here I'm going to get a gamma square minus 1 times m1 to the 4th power. So m1 to the 4th power times gamma square minus 1. And then I need to subtract minus 2 times gamma plus 1 m1 squared. And you see a lot of things drop out. So this goes away against that one. And this goes away against that one. And all that remains is a complete square, because now we have plus m1 to the 4th power, these two, minus 2 m1 squared, plus 1. Okay, so this is m1 squared plus 1 squared. Lovely, and then of course we can take the square root and everything is nice. So r plus or minus equals, the 2's cancel everywhere because I can pull the 4 out of the square root. Then I have m1 square gamma plus 1 plus or minus m1 square plus 1 from the square root divided by m1 square gamma minus 1 plus 2. Okay, now you see there is a boring solution and an interesting one. The boring solution is the negative one. Because if you take here the negative sign, you get m1 squared times gamma minus 1 . Sorry. I get m1 squared gamma minus 1 plus 2. So r minus is just 1. So r minus is the case without the discontinuity. That's not what we were looking for. Right? We know that in a fluid there may be no discontinuity. Okay, so r minus is the obvious solution. No discontinuity, that's just a smooth flow. So if we now continue to speak about r, we mean r plus. Now what is r plus? I get m1 square gamma plus 1 I have plus 1 minus 1. And I need to divide this by m1 square gamma minus 1 plus 2. That's it. Right? That's our jump. Now, what are the values for this r? First of all, the interesting case is, of course, that the Mach number m1 is larger than 1. Right? We have then a supersonic flow running into slower material. So let us assume that m1 is larger than 1, then we write this as gamma plus 1 divided by gamma minus 1 plus 2 over m1 squared. But now if m1 is larger than 1, this term here, 2 over m1 squared, is smaller than 2. If this is smaller than 2, then this is larger than gamma plus 1 divided by gamma minus 1 plus minus 1 plus 2, which is 1. Right? So if we have supersonic speed on the one side of the shock, then the density jump, or the density will increase in the shock. Okay. If m1 is getting very large, then this is going to go to gamma plus 1 to gamma over gamma minus 1. And this is a quantity that you very often find in the astrophysical literature. People say that, okay, we assume there's a shock, right, because the picture looks like that. And then they are going to assume this density ratio here, gamma plus 1 divided by gamma minus 1, mostly implicitly assuming that you have a strong shock here. And strong shock means that the Mach number is very much larger than 1, like here. Okay, what about the pressure jump? We carefully eliminated the pressure jump, right? But of course, now we can return to, for example, this equation here and solve it for Q. And I'm just searching for the simplest possibility to get a hold of Q. So I can use that equation here to solve it for Q. That's going to be m1 squared times gamma 1 minus 1 over r plus 1. That's going to be the pressure jump. And now, of course, you can take this ratio here, insert it here, do all the arithmetics, and find that under the conditions given above, Q is also larger than 1. So if you have supersonic flow, M1 larger than 1, then Q is also larger than 1. The pressure also increases. But Q is not, has no upper boundary now, because the pressure jump can be infinite. And then, of course, if you like, you can also calculate the temperature jump. And because you know the pressure jump, you know the density jump. If you assume an equation of state, then you can calculate the temperature jump. It's now not so interesting anymore. Yeah. But what I wanted to show you is that once you have a discontinuity and you assume that you have mass, energy, and momentum conserved across the discontinuity, across the shock, then you can directly relate the density jump to the Mach number, and then in the limit of large Mach numbers, this just becomes a function of the adiabatic index. And then, of course, you get all the rest from these equations. The conditions that you get in this way, right? This one for the density jump, this one that we have now not worked out for the pressure jump, the temperature jump that you get if you insert both into an equation of state, they are called the Rankine-Hugoniot shock jump conditions. Rankine-Hugoniot. Suppose you had a relativistic flow. It may happen once in a while. You proceed in exactly the same manner. And then you can also derive in exactly the same way the Rankine-Hugoniot conditions for the relativistic case. You know what the stress energy tensor and the energy current here look like in the relativistic case, and then you can work out these conditions on a problem sheet. Okay? So that's what I wanted to say. All I wanted to say about shocks. I think it is. Do you have questions so far? There was something more I wanted to say. Ah, yes. The shock itself is going to propagate. And what I wanted to show you is how we can calculate the shock speed itself. So let's briefly go through that. It's going to be a very short calculation. And in order to see how quickly the shock is going to propagate, let's create one. Right, let's take a tube. with a piston like that, filled with gas to the right. And now let's take a hammer and bang on the piston very hard. So this will instantly accelerate the piston to a velocity u when it was at velocity 0 before. And this will create a shock in the gas. So sometime up or somewhere upstream of the piston there will be a shock then. So this is supposed to be the shock front now. And we are going to have unperturbed gas on the right-hand side of the shock. So their velocity is going to be 0. And we will have gas that is driven by the piston, so we'll have velocity u on the left side of the shock. And now we want to know how fast is the shock going to propagate. And that's very easily found out, because now we transfer ourselves into the rest frame of the shock and then apply the shock clump conditions that we just used in the rest frame of the shock. And that's going to be it. So in the rest frame of the shock, we are going to have V1 prime equals V1 minus Vs. We will have V2 prime equals V2 minus Vs. But V1 is 0, so that's minus Vs. And V2 is u, so that's u minus Vs. Now we could directly say, okay, the shock speed is equal to negative V1 prime. That is related to V2 prime by the shock clump conditions. And then we can use that here. But let's say V2 prime minus V1 prime. This is going to be u. And now I'm taking V1 prime out of these two terms and get 1 over r minus 1. Okay, just applying the shock clump conditions that we had. So we know that V2 prime is V1 prime divided by r. So we have that. And now I just need to solve this for V1 prime, because V1 prime is the negative shock speed. So let us ask for minus V1 prime and get Ru divided by r minus 1. And now, of course, you can insert the r that we just calculated and see what the shock speed is. If you have a strong shock, right, if you can insert r equals gamma plus 1 divided by gamma minus 1, then you get here gamma plus 1 divided by gamma, divided by 2 times u. Okay? So since gamma is larger than 1, gamma plus 1 is larger than 2, so the shock speed is larger than u. So the shock starts running ahead of the piston, and the larger gamma is, the faster it does so. Okay? Just one application of the shock clump conditions now in order to find out how fast the shock is actually traveling. All right. What else? Now suppose you go through the following exercise. You say that V1 prime equals M1 times CS1. Then you solve this equation here for M1 and insert this here. You can directly relate the shock speed to the strength of the jump. Okay, in other words, you just eliminate the Mach number between the shock jump conditions and this expression here. All right, and then if you insert this limit here, gamma plus 1 divided by gamma minus 1, you will find that V1 prime is going to be, or the shock speed is going to be infinite. You shouldn't be surprised, because this is the limit of infinite, of an infinitely strong shock, for which the Mach number is arbitrarily large. All right, so that's what I wanted to say about shocks, right? The Rankine-Hugoniot shock jump conditions and the shock speed itself. Now, let us very briefly return to this expression here and now insert both the relativistic and the non-relativistic case for gamma. Right, just for illustration here. So now I'm going to use gamma equals f plus 2 over 2 for the non-relativistic case and f plus 1 over 2 for the relativistic case. You remember, right? This was because yeah, exactly. This was because we here in the non-relativistic case had a quadratic relation between energy and momentum. And in the ultra-relativistic case, we have a linear relation between energy and momentum. This is why there is a 1 here rather than 2 here. Okay, so in the non-relativistic case, for a monatomic gas, you have F equals 3 and gamma equals 5/3. For a relativistic gas, you have also have monatomic relativistic gas. You also have F equals 3, so this is sorry. Yeah, you have 5/3 here and you have 4/3 here. All right, let's insert this here. So in both cases, I can extend the fraction here by f. And then I get f plus. Let's make it more steps. Okay, we have f plus 2 divided by f plus 1 in the non-relativistic case divided by f plus 2 divided by f minus 1 in the relativistic case. I'm extending this by f, and I get 2f plus 3, 2f plus 2, sorry, and here I get divided by 2. I'm multiplying this, I'm multiplying both by f. I get f plus 2 plus f, that's 2f plus 2. And I'm getting here f plus 2 minus f, so that's 2. So this is just f plus 1 in the non-relativistic case. In the relativistic case, you see you have, I'm really creating a mess here. Okay, That's the relativistic case. And then I get here two F plus 1 divided by 1. Okay, for the relativistic case. So let us have a look at the non-relativistic case. First, if F equals 3, then there's a jump of 4 in the density. If you have a relativistic gas and F equals 3, then you get a jump of 7. Right? So first of all, if you analyze the strength of a shock, for example, from an image that you get, then you can directly infer, if you assume that you have a monatomic gas, whether you have a relativistic shock or a non-relativistic shock. That's one thing. The other thing is, suppose you let the shock run into different media for which the particles have different numbers of degrees of freedom, then the shock strength is going to change. Right? So this means that if you let a shock run, for example, into molecular gas, where, for example, internal degrees of freedom of the individual particles may be excited, then the shock strength may be much higher than that. Okay? Yes? Okay. The question was, if I start non-relativistic here, why can I pretend to be relativistic there? So this means that the shock velocity has to be non-relativistic. But this means that the internal motions of the particles can still be relativistic. Okay? And therefore, people often apply the relativistic limit here also to this condition here. All right. Do we have questions about shocks? There's a whole literature about shocks, of course, because you now can progressively complicate the analysis by, first of all, adding the relativistic case, then discussing oblique shocks, right, which are somehow inclined with respect to the fluid direction. You can have curved shocks, right, which will change the whole situation all over the place. Right? But the principle remains the same, and the principle I wanted to show you, you require conservation laws across these continuities. And then you do not need to solve the hydrodynamical equations, but you just apply the conservation laws and you get the Trump conditions out. Yes. Why are we doing the 2 divided by R1 spread? Exactly. So from here to there, we go to the limit of a strong shock, which means that M1 becomes very large compared to unity. Okay. So much for that. Resolving shocks in hydrodynamical simulations on the computer is a difficult problem, right? Because you know from the equations that there will be discontinuities. Discontinuities cannot be treated by sharp discontinuities, cannot be treated by computer programs. So they will ultimately have to resolve the shock, and therefore shock tube problems, right, are a generic test case for numerical hydrodynamics. And you set up a situation in which you know a shock will form, like here, and you test your code by asking how well does it represent, for example, the analytic solutions that you know. Good. So much for that. Let's have a break of 5 minutes, and then we move on with fluid instabilities. So there's a whole litany of fluid instabilities. I can't go through all of them. Very many of the fluid instabilities you can experience in everyday life. Let me mention a few of them. So, for example, there's the Kelvin-Helmholtz instability, which is also called the buoyancy instability. You can buy it on Christmas markets. You know these little boxes from plexiglass, right, that are filled with two fluids. One of them is lighter than the other. And the heavier fluid, if you leave it alone, is going to collect at the bottom. Now you turn this around. Right? You have seen that, I'm very sure. Right? And then the lighter fluid starts propagating upward. Right? If you only by a little bit perturb the boundary between the two fluids. For example, by shaking it a bit, you can't avoid that. Right? Okay, and then you see fingers of the lighter fluid propagate into the heavier fluid and downward as well. Right? This is called the Kelvin-Helmholtz instability. It's an instability of the boundary layer between the two under perturbations, and the perturbation leads to an exchange of the two fluids such that the natural order is re-established. Right? The heavier fluid has to be below the lighter fluid. That's Kelvin-Helmholtz. You see that everywhere. There's Rayleigh-Taylor. I'm messing them up. What I just said is Rayleigh-Taylor. All right, there's Kelvin-Helmholtz, which is a streaming instability. Right? You see that every time when the wind blows over the water. Right? You have a boundary layer between two fluids. That's the surface of the water. There is no wind, it's going to be plain. There is wind, it starts creating waves. That's the Kelvin-Helmholtz instability. You can combine both, right? Suppose you have a Rayleigh-Taylor situation, right? You have a lighter fluid below a heavier fluid, and then the lighter fluid will propagate upward in fingers, and the fingers can stream pretty fast, and at the edge of the fingers you will have a boundary layer between one fluid and another. This boundary layer can also become Kelvin-Helmholtz unstable, and then you get these eddies at the side of these uprising fingers. Sometimes you see clouds in the sky that look like this. It's not very often that you can see this, but once you see that there is a Kelvin-Helmholtz instability between two layers in the atmosphere. Sometimes when you see one stream running into another, right, and you can distinguish the water because one of them is more clear than the other, you can see a Kelvin-Helmholtz instability at the boundary layer between the two fluids. It's everywhere. If you stand on the beach, maybe you did that in the summer, waves are coming. And then when the waves propagate towards the shore, of course they run into shallower and shallower water, and then they break. Why do they? Right? It's another kind of instability, so-called gravity wave instability. Don't confuse them with gravitational wave instability. That's a different thing. All right. So if you look around yourself, you find fluid instabilities everywhere, right? In the atmosphere, in the water, and so on and so forth. Now, I would like to use the Rayleigh-Taylor instability, the buoyancy instability, just for one example, because the analysis of these instabilities is proceeds always in the same manner. What do? Number one, you linearize the relevant equations. Number two, you decompose the perturbation into plane waves. Once you have linearized them, you know you can do that, right? Because by superposition of plane waves, in other words, by Fourier transform, right? You can model almost any perturbation that you have in mind. So you decompose the perturbation into plane waves, and the plane waves are characterized by a wave number and by a frequency. This gives you then the equations that you apply give you a relation between the frequency and the wave number. This is a dispersion relation. Right? Relations between frequency and wave number, dispersion relations. Dispersion relations allow you to decide, does the frequency square become negative or positive? Right? If the frequency square is positive, and you know that there is a real frequency and you're going to have oscillations, and this signals stability. However, if the frequency square becomes negative, you know that the frequency is going to be imaginary, and instead of trigonometric solutions, you will have exponential solutions, and that signals instability. Okay, so once you have the dispersion relation, you search for where is omega square going to change sign. And this signals the onset of instability. And you know, we did that already. Right? When we derived the criterion for Jean's instability, we did exactly that. Right? We saw where does the frequency or the time change of a perturbation, its square change sign. All right. So let us first take the hydrodynamic simulations in a simple case, hydrodynamic equation, sorry, in a simple case and linearize them. So we had continuity. Let's ignore gravity for now. It's going to come in later. And the Euler equation. Now I'm going to do exactly the same few steps that I did when we started analyzing sound waves. What did we do there? We imagine we decompose the velocity into an unperturbed velocity v0 and the velocity perturbation. We do the same thing with density and pressure. And then we transform, we beam ourselves into the rest frame of the fluid. In other words, we start swimming with V0 along the fluid. So that's just by Galilei transform. And then we linearize the equations. In other words, we drop all terms that are going to be quadratic or of higher order in the perturbation. And then what remains is at 0th order dt rho 0 equals 0. Right? Because the velocity here is already of first order. And so everything I can do here will never be of 0th order. So dt rho 0 is 0. Okay. This term can only have a combination of V0 and delta V. But V0 is 0. So this is going to be 0 all the time. At 0th order, this tells you that dt v0, well, this is 0. But then it tells you that the gradient of P0 must be 0 as well. Right? There cannot be a pressure gradient in the unperturbed solution. All right, let's go to first order then. Then I have dt delta rho. Now, since there is no 0th order in the velocity, I need to reserve the first order for the velocity perturbation here. So this will turn into plus rho 0 times the divergence of the velocity perturbation. All right. If I take this to be your first order, still this will not appear. Because V0 has no gradient. And if I take V0 on the other side, it's going to be, to set this to 0 anyway. So this will be dt delta V plus, now, gradient delta P, but then I need to divide by rho 0. That's going to be 0. And this is the reason why I looked at these equations again. Right? Because here, now, the pressure gradient appears, but divided by rho 0. And this has consequences for our specific enthalpy. Remember, we had the differential of H tilde is dP over rho. But now, in a first order perturbed system of equations, this does not have dP over rho, but dP over rho 0. But this is dP over rho 0, right? Because there is no change in rho 0. So I can replace the specific enthalpy by P over rho 0, or rather, P over rho 0, instead of an integral over P over rho 0. And with this information, we now return, in the first equation, you mean? Yeah? Because delta P is already a first order. So if you remain at first order, that's all we have. And then the enthalpy is just given by that. All right. Now with that information, let us return to Bernoulli's equation. And remember, how did we get Bernoulli's equation? Well, we took Euler's equation. Let me take it again. And now let me add the gravitational field again. Now we approximate this, first of all, linearly. And we know that this term is going to disappear. We approximate this linearly, and we see that rho 0 will become a constant at first order. Remember, when we derived Bernoulli's equation, we just assumed, okay, we have a stationary flow. Now, of course, we want to have a perturbation of a fluid system, and then we cannot assume anymore that we do not have a time derivative. But in order to simplify things, we will assume that we have a potential flow. In other words, we assume that there exists velocity potential psi such that the velocity is the gradient of that. This is no surprise. Helmholtz theorem guarantees that psi exists. The core of this assumption is something else, namely that there is no curl. Right? So we assume that there is a flow which has no curl. Right? Curl V equals 0. All right, that's the core of the matter. This is not surprising. Right? The lack of a curl is surprising. All right, but if we take a situation like that, then we can write gradient dt psi plus P over rho 0 plus phi equals 0. Okay, because then we can pull the gradient out of all of these expressions. And remember, for doing that, we had to neglect this term, which we can do at linear order. And here I'm not writing delta p or delta phi anymore, so that all the quantities p, phi, psi, and so on are assumed to be small. Okay? So this is Bernoulli for a time dependent situation, but for a velocity field that has no curl. And if you want, you can apply the same arguments to the complete Euler equation without the approximation. If you write this term here in terms of the vorticity. But I don't want to do this right now, right? Because I'm driving towards a linear analysis. So this means that dt psi plus p over rho 0 plus phi equals some constant. And now, of course, we need to specify further that this is a constant in space, right? Because we have taken a gradient here. This does not mean that this is a constant in time. So this may be a function of time. So let me gauge the velocity potential in the following way. Let me say I'm going to replace the velocity potential by this. Okay? If I do that, then I do not change this relation, which is the only one that I care for. But then I can write dt psi plus p over rho 0 plus phi equals 0. Right? Just by re-gauging this velocity potential. Okay, lovely. Now we have a Bernoulli equation, which is of limited use, right? Because we have linearized the equations and because we have assumed a non-vortical flow. But nonetheless, right, we can now use that for further analysis. I'm going to use that in the following form, namely p equals minus rho 0 dt psi phi, and rho 0 is the unperturbed density. Obviously, right, because here it's multiplied by weak perturbation. So for this equation to be first order, rho 0, we have to insert the unperturbed density here. Okay. This is a very important equation for linear stability analysis of fluid situation. Now, you can play all kinds of games with that, but let us now apply this to the Rayleigh-Taylor instability. So the situation I have in mind is the following. This is the box, the plexiglass box that I buy from the Christmas market. And here is my z-axis, opposite of gravity. So I'm assuming that there's a gravitational acceleration pointing down. I have to remember how I did this in the lecture notes. I think I called this part 1 and part 2 of the fluid. I'm assuming that for the unperturbed fluid, this is the 0 line, and I'm just calling this the 0 point of the z-axis here. And now I want to perturb this a little bit, for example, by shaking the box. And I want to know, is that surface now stable or is it unstable? Let's see. All right, so what do we know? Wait a moment. I'm calling this h1. I'm calling this minus h2. I'm calling the perturbed surface zeta, right, to have a Greek set. And zeta will, of course, be small, right? This is by our assumption. And zeta will be a function of x and y. I will tell you by how much I will distort the boundary layer between the two parts of the fluid that was at z equals 0 before. Okay, what do we know? We know the following things. There should be pressure equilibrium. There should be pressure equilibrium at the surface. This is just the mechanical condition for there being no force between the two layers here. Okay. dz psi1. So, of course, now I can describe the velocity perturbations by perturbations of the velocity potential psi. And I will have to distinguish between psi1 and psi2. So dz psi1 by definition is the set velocity which I want to evaluate at the boundary. And that, of course, must be the same for both. Because if it is a contact layer, it must move in the same way for both. Okay. And I also know that dz psi1 at z equals h1 must be 0. In other words, the fluid remains in touch with the top. And the same must hold for the bottom. So that is at minus h2. All right, these are the boundary conditions that we have to satisfy. In addition, I want to assume that I have an incompressible fluid. Divergence V equals 0. So that's going to be the Laplacian of psi. In other words, the velocity potential psi is required to satisfy the Laplace equation. All right. So the equations we have to satisfy are these here. It's not a nice number. No, it's okay. So the two equations that are boxed in the bottom line, these are the equations we have to solve. All right. Of course, the Laplace equation is already linear, so we don't need to linearize that. So we have satisfied the first step. We have linearized our equation. Next step was that we set up boundary conditions. Next step is, as I said before, we now decompose the perturbations into plane waves. So I'm going to make an ansatz for psi. And the ansatz for psi is that it is some function f of z, which I don't know yet, that I have to determine according to the boundary conditions, and a plane wave. And for simplicity, I'm going to assume that the plane wave is propagating along the x directions. In other words, I'm rotating my box such that the perturbation is running in x direction. Just for simplifying that, right? Otherwise, you get a wave vector here, which would complicate the analysis just a little bit, but not very much. It doesn't matter, right? We are free to rotate that box. Okay, now, what do we know? First of all, we have to satisfy the Laplace equation for that velocity potential. So what does that mean? There is no y dependence. There's just an x and a z dependence. If I apply the Laplacian to psi, that's going to give me an f double prime if I take the derivative with respect to z, and since f only has the z argument, I denote the derivative with a prime. Let me write it like that, f double prime over f, so that I can write that the double set derivative of psi is just f double prime over f times psi. Okay, if I apply the double x derivative to that, I'm getting minus k squared. Now this has to be 0, right? F double prime over f minus k squared times psi equals 0. For arbitrary psi, I can satisfy this only if f double prime minus k square f equals 0. And you see f has to satisfy an oscillator equation with a negative frequency squared. So in other words, what I'm going to get as independent solutions are exponentials in z. So f equals exponential plus or minus kz. Now, of course, for a general solution, I need to superpose the positive and the negative branch. So I'm going to write f equals a times e to the kz plus b times e to the minus kz. And that's it. Of course, I will have two of these functions, right? Because I will have two of these potentials, psi 1 and psi 2. But now, let me see what this condition here implies for f1, for example. So let me look at the case f1 now. And if I take the set derivative of psi 1, it only will give me an f prime of z times this phase factor here. But the phase factor will not become 0. So this means that f prime, f1 prime at z equals h1 must be 0. Right, in order to satisfy this condition here. And likewise for that one. But this immediately implies that a1 minus b1 must be 0, right? If I take the z derivative here, I'm going to get a factor of k down from here and a factor of minus k down from here. And I will have, oh, sorry. A k times a1 times e to the power of k1, k h1 minus b1 e to the power of k times h1. This must be 0. At the same time, I know that I have to satisfy these criteria, right? The set velocity at the perturbation must be equal. So, okay, from that condition here, I see that these must be equal here. And now, since psi has to be a small quantity, because we have linearized the equations, the amplitudes A1 and B1 have to be small quantities. But then I need to evaluate the exponentials at z equals 0 in order to remain at first order in the perturbations. So this tells me that k a1 plus b1 equals k a2 b2. All right, there's a negative sign missing here. All right, now I can satisfy these conditions if I set B1 equal to A1 and at the same time require that e to the power of k times h1 equals e to the power of minus k times h1, which is the case when e to the power of k times h1 is 1. Okay, so I can satisfy this if I say A1 equals B1. And then if I require that e to the power of kh1 is e to the power of minus kh1. If that is the case, or if I choose the constant such that I can write, then I can write f1 is a1 e to the power of kz plus h1 e to the power of kh1 is just 1, right? So I can multiply this in. And I get e to the power of minus k z plus h1. Right, so by this choice of the constants, I can satisfy the first of these conditions here. And then you see that I can write f1 just as a constant, let's call it small a1 now, because there will be half the big h1 times the hyperbolic cosine of k times z plus h1. Same for f2. If you replace plus h1 by minus h2, and set f2 equals a2 times the hyperbolic cosine k times z minus h2. All right. Good. Now, if I now take the second condition here, oh, wait a moment. We need to rederive this here. So now I'm going to return to this condition here and take the derivative of f1 and f2 with respect to z. So dz f1 taken at z equals 0, this is going to be now k times a1 times the hyperbolic sine of k times h1, right? Because we need to set to 0 here, and dz f2 at z equals 0 equals k times a2 times the hyperbolic sine of minus k times h2, and that's going to change the sign here, right? Because the hyperbolic sine is asymmetric in this argument. All right, so this here will relate the two amplitudes to each other. The hyperbolic cosine for the functions f1 and f2 comes because we have boundary conditions at finite depth and at finite height. Right? If you shifted the depth to minus infinity and lifted the top to plus infinity, then we would have only exponential functions here. Okay, now we know pretty much what f1 and f2 are. Now let us return to the first boundary condition and use Bernoulli's equation. So now I'm going to take this boundary condition here and I'm going to use that the gravitational potential is just given by g times zeta. Yeah. Because we have a joint boundary layer for both, right? And k is the wavelength of the perturbation, and this must be the same on the top and on the bottom for the fluids to remain in contact here. Okay, so I'm assuming that yeah. All right, yes. That's true. Sorry. All right. Good. Now, let me briefly write down how this would proceed, and then we stop. So now I need to satisfy this condition here. So I'm going to write P1 equals minus ρ1, that's the unperturbed density on the one side now. Now I have dt psi 1, and I have plus g times zeta. And this must be equal to minus ρ2 dt psi 2 plus g times zeta, because of course the height zeta is the same for both. So in other words, I can write here an equation for zeta which reads ρ1 dt psi 1 minus ρ2 dt psi 2 divided by g times a ρ2 minus ρ1. Okay. This is the first time that we are now using a dynamical equation, right? Bernoulli's equation. The first time where we use the hydrodynamical equation. All right. Now the way how this proceeds is the following. We take another time derivative of z. What does that mean? This tells you by how much the boundary layer is going to move. But z is the elongation above and below the unperturbed fluid level. So that must be equal to the z velocity here. So if I take another time derivative of zeta, I'm just getting second time derivatives on the velocity potentials here. And at the same time, I know that this is Vz, and this must be equal to dz psi 1 at z equals 0, and must be equal to dz psi 2 at z equals 0. Okay. This z derivative here will give you a wave number. These time derivatives will give you a frequency. So this combination here is the dispersion relation for the Rayleigh-Taylor instability. And then you will find the not surprising result that omega square will become negative if rho 2 is less than rho 1. Right? Because if rho 2 is less than rho 1, the frequency squared will become negative. And then you know that the boundary layer is going to be unstable. All right. This was a bit of a rush, and we are running over time right now. But what I wanted to show you is the principle of this kind of analysis. Right? You start with a linearized equation. In our case, the linearized equation is this linearized version of Bernoulli's equation. And we linearized Bernoulli's equation by getting rid of this term here, which would have been second order. But at first order in the perturbations, Bernoulli's equation shrinks down to this little piece here. And since we assumed a non-vortical flow, we know that there must be a velocity potential, which for an incompressible fluid must satisfy Laplace's equation. And all the rest was a decomposition of the perturbation into plane waves and inserting this ansatz into the boundary conditions at the top and the bottom at the boundary layer, like these two. That's mechanical equilibrium between the two fluids. This is velocity equilibrium, and the velocities must be the same. And this is that the fluid must be at rest at the bottom and at the top. Okay. Then we made an ansatz for psi, decomposing it into a plane wave and the function f of z, which we need in order to control the boundary condition. This means that we need to write f1 and f2 essentially as hyperbolic cosines. Right? We could choose differently, but this is a really straightforward ansatz for this case. Then we inserted this into the Bernoulli equation and enforced the remaining boundary condition here in order to derive at a dispersion relation for these waves, right? A relation between omega squared and the wave number. And if you go further here, you will find that omega squared is negative if the lighter fluid is on at the bottom of the heavier fluid. Okay? This will return every time now, right? In plasma physics, in magnetohydrodynamics, it appears everywhere where you need to do an instability analysis. And you always proceed in the same manner. Right? You linearize your equations, you decompose into plane waves, you find a dispersion relation, you see where the frequencies become positive or negative. And this is what I wanted to show you. Right? The result is not surprising at all. Right? Of course, you know that when the lighter fluid is below the heavier fluid, you will get this kind of instability. But I wanted to demonstrate in one example how you proceed there with the calculation. All right. What is it today? Wednesday, right? Then we meet again next Monday over there in Neuenheimerfeld at our usual lecture hall. And then we will start talking about plasma physics. Right? Because now we have completed 3 weeks of hydrodynamics. But of course, the concepts of hydrodynamics will reappear as we go through plasma physics then. All right? See you next week.